So we've said that we can look at stars, we can measure their distances, and if we know how bright they are, we can work out how far away they are. And likewise, if we know how far away they are, we can work out how bright they are. So let's try and look at this a bit more formally. So we're going to look at two things here: the apparent magnitude of the star, that's how bright it looks to us, and the absolute magnitude of the star, that's a measure of how bright it really is. We need to start off by looking at luminosity and brightness and define those two terms. Then we need to define this scale called apparent magnitude, which is a rather confusing scale for historical reasons, and then we need to relate that to the absolute magnitude. So first of all, luminosity and brightness. So luminosity of a star is its total power output. The brightness, this is to do with how bright it's going to look to us, depends on how much of that light is actually reaching us, and that just depends on how far away we are. Okay, so we're at some distance, which is a sphere of radius r away from that star. So the amount of energy that reaches every square meter where we are is the total amount of energy that's radiated by the star divided by the surface area of that sphere around the star that we're on the surface of. So for example, the sun, which is obviously going to create quite a lot of power at the surface of the Earth, it's going to be very bright to us, has a power output of 3.8 times 10 to the 26 watts. So its brightness of the Earth can be worked out by this equation. We simply do the power, we divide it by 4 pi r squared, and that gives us 1340 watts hitting every meter squared. Obviously for every other star in the universe, that number is going to be a lot smaller. A little bit of trickiness in this, in that if we're talking about brightness in terms of us looking at it, then we're only talking about the visible part of the spectrum, so most of that energy will be not in the visible spectrum. Okay, so here comes the tricky scale, apparent magnitude. It is, as it says, a bit complicated for like so many things in astrophysics for historical reasons. Okay, it comes from this guy Hipparchus, who was the first person to try to look at the stars and put them into groups according to how bright they looked. He did groups which made 1 the brightest star and 6 the faintest stars that he could see back in the 2nd century BC. Okay, so we've got all stars on a scale 1, 2, 3, 4, 5, 6, from the brightest ones being 1 to the faintest ones being 6. Notice this is part of the problem where we start, that the brightest stars have lower numbers than the faintest stars. Later on, people actually could measure the brightness of stars rather than just looking at them, and they realised that the brightest stars were about 100 times brighter than the dimmest of these stars. So this gave us a scale going from 1 to 6, which actually had a difference of a factor of 100 in the brightness. Various things happened to try and standardise this as science got more precise in its measurements. Okay, but the crucial thing is this number 2.5 comes from, if you take this star and you go to magnitude 5 will be 2.5 times brighter, magnitude 4 will be 2.5 squared times brighter, and so on. If you do 2.5 to the power 5, you get about 100. Okay, 2.5 is a little bit of a rounded number, but it's near enough. Okay, so let's have a little look at an example. This is the constellation Orion, the Hunter. Okay, it's got 4 bright stars at its corners, and Orion's belt in the middle, and a sword hanging down here. Just going to look at a few of these stars. Which one's the brightest? Well, according to how it looks to us, so the question now is which one looks the brightest. Okay, here's Betelgeuse up here with a magnitude of 0.45. Here's Rigel down here with a magnitude of 0.18. Just stop there a second and think which one of those is actually brightest as we see it. Well, the one with the smaller number is going to be brighter. Notice these are both brighter than a magnitude 1 star, because of some changes since Hipparchus' system. A couple more stars for us to look at in here. Bellatrix with a magnitude of 1.64, so that's a bit more than 1 below that, so that's probably about 3 times as dim. So Betelgeuse is 3 times brighter than Bellatrix roughly. and Hatsia, which has got a magnitude of 2.77. So you'll notice that's another magnitude down, so another 2.5 times dimmer than Bellatrix. Okay, so we need a bit of a scale to relate the brightness to the apparent magnitude. So we've talked about these steps of 2.5 times. Okay, so this gives us this equation here. The magnitude is minus 2.5 times the log of the brightness. This brightness is not in the kind of units we used before. It's relative to a star that we define as having a magnitude 0, because then the brightness of the star divided by the brightness of the star we're comparing it with, this will be 1. Log of 1 is 0, so this will give us a magnitude 0 star. So just to see if we've got that, in magnitude 1 star compared with the magnitude 3 star, it's 2 magnitudes brighter. Every magnitude represents 2.5 times brighter, so the difference is 2.5. 3 minus 1 is 2, so it's 6.25 times brighter. Remember again, the magnitude 1 star is brighter than the magnitude 3 star. Okay, if we compare the full moon, which has got an apparent magnitude of minus 12.8, notice a negative number here means it's very bright in the sky, compared with Vega, which has got a magnitude of approximately 0. Okay, if we do the maths on there again, the difference of 12.8 means it's 124,000 times as bright. So it only goes from 0 to 12.8. It doesn't look like that much of a change maybe. That's 124,000 times brighter. If we compared the Sun with the full moon, we've got a difference from minus 12.8 to minus 26.8, so it's 14 magnitudes brighter. Okay, 2.5 to the power 14, it's 370,000 times brighter in the sky than the full moon. Okay, so that's sorted out for us how bright things look, but the crucial question is, how bright are they? So this is absolute magnitude. The capital M there tells you that we're dealing with something which is the same for any observer around the universe, as opposed to the little m, which was just how we see it. People on a different planet somewhere else might see it as a different brightness. Okay, so there are two things which tell us the apparent magnitude. One is to do with how bright it actually is, its absolute magnitude, but the other one is to do with how far away it is. What we could really do with is some kind of sort of fair test. So we move all stars to the same distance from the Earth, and that allows us to compare their actual brightness. So we need some point where we can say, let's move to this point, and it just so happens that they use a distance of 10 parsecs. Remember, a parsec is 3.26 light years away, so we're 32.6 light years away from the Earth. And if we could take all the stars in the universe and park them there, we could look at them from the Earth and we could have a fair test to see which one really is the brightest. Okay, those are called the absolute magnitudes. Okay, now we've got three things in the equation, so if we know the distance to a star and its apparent magnitude, then we can calculate its absolute magnitude. Okay, the magnitude though will decrease as a square its distance, so if we take it further away, if we took it twice as far away, it would only appear a quarter as bright. To be a bit more general about that, if we took it a distance d parsecs from the Earth and then we dragged it to 10 parsecs from the Earth, it's going to look d over 10 times brighter. So just for example, if it was 30 parsecs away and we moved it to 10 parsecs away, it's going to be 30 over 10 squared, 9 times brighter. Okay, so if we take a star that's more than 10 parsecs away, it will appear brighter as it comes towards this point where we measure its absolute magnitude. Okay, so that's going to give us an equation which relates the apparent magnitude little m, the distance d, and the absolute magnitude big M. The way we do that is we've just said that its brightness at 10 parsecs is its brightness at the distance it actually is, d, times d over 10 squared. And we've also defined its magnitude as minus 2.5 times the log of its brightness at the distance d where it actually is. If we want to work out its absolute magnitude, then we want to know minus 2.5 times the log of its brightness at a distance of 10 parsecs. So if we take this B10 and we substitute in this value, then we get minus 2.5 log of BD times d over 10 squared. That's the physics. Now we have to just do a little bit of tricky maths for it. So what I can do is I can take this is log of a times b, which is log of a plus log of b, so I can split this log into two parts. Once I've done that, what I can say is, look, over this side I've got minus 2.5 log BD. Well, we knew that, didn't we? It's up here. That's little m, so this part is its apparent magnitude. If I take the minus out here, I get minus 2.5 log of d over 10 squared, but this is log a to the power n is n log a, so I can take the 2 and multiply it by the 2.5, and that becomes a 5 log d over 10. I just move the signs around a little bit, so I take the m over that side, and then I swap these round to get rid of that minus sign. This is the equation we need. The apparent magnitude, take away the absolute magnitude, is 5 log d over 10. Looks like quite a strange equation, but at the end of the day, it's three unknowns, one equation. Okay, if we know two, we can work out the other one. So if we go back to our friend Orion, and we look again at these four stars, okay, we've got on their distances, which we might have measured by parallax perhaps. So Betelgeuse is 197 parsecs from the Earth, Bellatrix is only 77 parsecs from the Earth. Hatsia, even though we said it's the dimmest star, is 700 parsecs away from the Earth. So it's about 9 times as far away as Bellatrix. So if they were the same brightness, it would only appear to be 1/81st of the brightness. Here's Rigel. Rigel's further away than Betelgeuse, much closer than Hatsia. So have a little calculation, see if you can work out from that the absolute magnitude of the stars. Okay, here they come. So Betelgeuse has an absolute magnitude of -6. Notice that's much higher than where it starts from. Okay, because it's 197 parsecs away from the Earth, and we're dragging it to 10 parsecs away from the Earth, so it's only a 20th of the distance away. It's going to be 400 times brighter if we could park it there. Okay, Bellatrix has a magnitude of -2.8. Hatsia, you'll notice, is a long way away, so in fact, what we find is that Hatsia is actually a brighter star in terms of its absolute magnitude even than Betelgeuse. Okay, but it does actually still turn out that Rigel is the brightest of all these stars. Okay, it's got an absolute magnitude of -6.9.